Hello, I'm Nick. As promised, I'm doing at Code Regular Contest 203 with commentary. Five problems. Problem A, all winners. And teams are participating in a team shogi tournament. Each team consists of M players. This tournament is a round-robin format with a total of all the matches played. In each match, the M players from each team are randomly matched against each other, and one player always wins while the other loses. After all matches are played, each player will have played exactly N-1 games, and players who won all their games will be awarded the perfect record prize. Find the maximum possible number of players who can be awarded the perfect record prize. Okay, so if M is even, we can just split every team into winner half and loser half, and in every match just match winners from one team with losers from the other. Then exactly half of the players will win all their matches, and that's obviously the maximum possible. Can we do better than that? I think no, because no, like for even it is obviously the optimal. For odd, I think the optimal would be to have like half rounded out for every team, and one team will have one more player that wins everything. And the reason for that is that let's just look at how many players on every team will win all their matches. And let's call those numbers like A1, A2, and so on, AN. Then for every two different teams, the sum of those numbers must be at most M. Because otherwise, in their head-to-head match, we will have more than M winners. That's impossible. So, since M is odd, okay, either all those numbers are not greater than M over 2 rounded down, which is worse than what I'm suggesting, or there will be one number that is strictly greater than M over 2 rounded down, but then all the, like, let's call it X, but then all the other numbers must be not greater than M minus X, because sum of those two must be at most M. Yeah, it should be pretty clear that the best possible we can do is make that X to be like M over 2 rounded up and all others rounded down, and that's that's the upper bound, and we can achieve it by like for odd M we like doing the same, but there is one player left on each team, and they just like the strongest always wins, something like that. Like one of them will win all their matches, and the rest will not. But in the other players, like exactly half will win all of their matches. So if M is even, the answer is n times m divided by 2. And if m is odd, then it's n times m divided by 2 round down plus 1 for that very special one guy. problem be swap if equals sum. Given lengths and integer sequences A and B, each consisting of zeros and ones. Let Aij denote the consecutive subsequence of A from I through J's element. If I is greater than J, then it's an empty sequence. You can perform the following operation on A any number of times. Choose for integers A, B, C, D that satisfy the following two conditions. So the sorted and B is strictly smaller than C, so I'm assuming it's like a segment from A to B and a segment from C to D. And the sums on those segments should be the same. Okay. Then we swap those segments. Determine whether A can be made to match B. Interesting. They consist of zeros and ones. So the sum is actually the number of ones. Interesting. We can swap two segments. Okay. So we have a sequence. What does it mean to swap the segments? I replace A with a sequence formed by concatenating the prefix, then the second segment, then the middle part, then the first segment, and then the suffix. Okay. That's what I expected. So we are taking two segments. Are we allowed to make those segments empty? No, we are not. Okay. We are not allowed to make them empty. It's in the interesting, like, special kind of case. So taking this segment and this segment, and then we're swapping them. Okay, so let's try to see what simple. How did I do that? Probably. Okay, so it can get smaller but not bigger. That's interesting. Okay. So yeah, I think if we have like two ones, we can do a lot of things. So if we have like some zeros, then ones, and more zeros, and ones, and more zeros, I feel like we should be able to pretty much achieve like every permutation. Because like we can take this one, and then we can take like some segments that contain this one, and then swap them, and that would kind of like rearrange zeros between those ones. Like, let's try to achieve like ones in two leftmost positions. So taking like segments like this, swapping them, it will be this, and then taking this one now and this thing, swapping them, and we will get no, actually that's not what we're getting here, but it doesn't matter, like, right, it will be like this one, then some number of zeros, and one, and then some number of zeros, and then we will just take this one and all the zeros up to this one, and just this one, swap them, and we will get like 1 1, and then all the zeros. But also all the operations we are doing are undoable. So if we can get from some state to some other state, then we can go back. And since like I have shown that with 2 ones I can move them like I can move them to the front, that means that I can move them anywhere, because like from the state that I want to get to, I can get to the state where the ones are in the front. So now I can reverse those sequence of operations. And so if I have 2 ones somewhere, I can move them to the front and then move them anywhere I want. Okay, so if I have 2 ones near each other, like I can basically like take the largest segment that contains them and then place those 2 ones anywhere. Obviously, the number of ones is not changing. Like the final array will be the permutation, even if it wasn't like just zeros and ones. But since it's zeros and ones, it just means that the number of ones will stay the same. So if I have 2 ones, I can move them, and that probably means that like if I have at least 2 ones, I can do any permutation. Basically, like look at the first 2 ones, move them to the front, then second and third move to the front, third and fourth move to the front, and so on. So I can move all the ones to the front, which means that like from any permutation with this number of ones, I can move them to the front, and then it means that I can reach any other state from that. So I can permute them how I want. Okay, so the number of ones stays the same. If it is the same and at least 2, then the answer is just yes. I don't need to print the sequence of operations, I just need to say yes or no, right? Okay, great. Okay, so if the sums are different, no. If the sum in one is at least 2, then yes. So other cases I need to solve is like there are no ones in both and there is one in both. If there are no ones, then they're just all zeros and they are the same from the start. So the answer is yes. And if there is just one, well, here like it becomes a bit interesting, because like I cannot touch that one, right? So I have some zeros. I cannot touch it because if I put it in one of the segments, the other will have some zeros, so I cannot swap them. So I can only swap like some segments of zeros. They must be non-empty. It doesn't make sense to make the swap like on the same side. If I take 2 segments of zeros on the left of one, I swap them, like the rest is the same. But if I take a segment on the left and on the right, swap them, something will change, probably. And it seems that if I have both parts non-empty, I can make any non-empty thing. Like, if I want left part to be 1 0, I just take 1 0 here and all the zeros on the left, and then I will have like 0 1 and all the rest of the zeros. Right, but if left part is empty, then I cannot make any like non-trivial operation, and the same if the right part is empty. So if the sums are 1, I need to check if the 1 is like the first one, the last one, or somewhere in the middle. And like those three cases will stay the same. Okay, that's enough to solve the problem. Right? Okay. So I'm calculating the number of ones and the position of the last, because if it's exactly 1, I will need to know the position. It doesn't have to be the last one, just I can calculate like sum of positions, the first one, the last one. Just need the position of that only one if the sum is 1. The same for the second array. If A is not B, return false. If A is not 1, return true. Otherwise, I need to check if it's like if it's the first, the last. There is potentially something if n is 1, because like first and last are the same, but since I wrote those ifs in the same way, it should be fine. Problem C, destruction of walls. Rooms are arranged in a grid with h rows and w columns. There are walls between adjacent rooms that share an edge. When you are in a room A and room B is adjacent to room A in one of the 4 directions, up, down, left, right, and the wall between room A and room B has been demolished, you can move from room A to room B. Find the total number modulo of ways to choose k walls such that the following condition is satisfied. When all chosen walls are demolished, it is possible to move from the top left room to the bottom right room by passing through some rooms, and k is at most h plus w. To get from one corner to the other, we would need to make h plus w minus 2 steps if we just go like right and down. So like at least h plus w minus 2 walls must be demolished. So this seems like some case bash inclusion exclusion, because like we don't have a lot of leeway. And well, case bash, but there are not a lot of cases, I guess. So like we need a pass. We need to demolish all the walls like on that pass, and maybe we will have like 2 more walls to smash. So like it is tempting to say that the answer is like choose like number of ways to choose a pass, which is binomial coefficient, like multiplied by the number of ways to choose like additional walls to demolish. The problem with that is that we can count something several times if like there are several paths possible, but that is like very infrequent occurrence. Like basically if you draw like 2 paths that need to be demolished, like they will differ by at least 2 walls. So they must differ by exactly 2 walls, and we cannot demolish anything else. But that happens only if you like go to some point, then one path goes down and right, and the other path goes right and down, and then they continue the same. So basically, the things we will count twice are like those combinations. We just need to count the number of ways to do that. So basically, we're choosing like this point where we will have like this small fork. So agreed. The number of paths is like h plus w minus 2, choose h minus 1. I guess I also need like total number of walls in this scene, which is in every row we have like w minus 1 walls, plus in every column we have h minus 1 walls. So that's the total number of walls. Let's call it A. So after I chose the path, I need to multiply it by the number of ways to choose like additional walls. Additional walls, like number of options for them is like A minus the number of walls we destroyed, which is this. And I need to choose K again, how many walls I have left to destroy, which is K minus this. Like for this thing I will pre-calculate factorials here, like this bottom thing is at most 2, so I just calculated with a couple of ifs. Right, and if k is equal to h plus w, then it is possible that I choose like this. So I will destroy like this pass and those two walls, but I calculated twice because it is also can be viewed as like choosing this pass and destroying those two additional walls. So I need to subtract those things. Basically I need to like collapse this, calculate the number of so like why the number of pass was this, because like we need to do h minus 1 moves down and w minus 1 moves right, and we can do it them in any order. In this situation there will be like h minus 2 moves down, w minus 2 moves right, and there is also one square that we can put at any place. So I'm choosing any permutation of those three moves, and like every permutation will correspond to this pair of paths. So their number is like sum of all the three plus w minus 3 factorial divided by h minus 2 factorial and by w minus 2 factorial and by 1 factorial, which is just 1. So yeah, the answer is this minus this. So if it's 1, then I just need to multiply by this number, which is 2 times w times h minus 2w minus 2h plus 2. And if it is 2, then I need to multiply by this, and then by the same thing minus 1, and then divide by 2. And also subtract plus m minus 3 That is wrong. So it should multiply by 2. Alright, I forgot to multiply by 2 here. And here. That is incorrect. I don't like this. Let's help. Oh, there is probably like non-optimal passes also, right? Like I was only counting the shortest pass, but since we have 2 more edges, it doesn't have to be the shortest. It can go like something, then like go right, down, left, down. and then go forward. And like similarly with okay, that's not how I should draw it, right? I should start from the unoptimal move. No. Okay, like goes left. Before this left, it must go down. Otherwise, like there is a path to this point before, and that's not good. So it goes down and then in some way, and like the transposed. So like at some point it will go up. Before that it should go right, and after also right. And optimal here. Like I again want to compress this and but like there is a small issue that after this point there must be a move right, and before this point there must be a move right, at least one. Oh. I can't even do linear time, right? Like W are up to 200,000 because we need to calculate factorials, but the sum is not bounded, so I need like constant time or like logarithm time formula. Okay, I think it's not such big deal. I can look at it as follows. So I have this thingy. I need to do W steps right other than this thingy, because this is like one step left, but I need to shift by W minus 1, so I need to do additional to my one step left, I need to do W steps right, and the other like H minus 3 steps will be down. This thing moves by 2 down, and I need h minus 1 in total, so I need h minus 3 more steps down. So first, let's choose the order of moves right and this thing. And we know that this thing cannot be before all steps right or after all steps right. So the number of ways to choose that will be like w minus 1. Basically, like put all the steps right, there are w of them, and now we need to insert like this 3-step thing in between of 2 of them. There are w minus 1 positions. Now I have a sequence of w plus 1 operations, and I need to interleave them with those. So that's another binomial coefficient, like w plus 1 plus h minus 3, choose h minus 3. So w plus h minus 2, choose h minus 3. And that's the number of those, and the symmetric thing will be the number of those. Tricky. Okay. I didn't technically need to write this if, because like this will return 0 because of how I wrote it. Like if that parameter is below 0, it will just return 0. Okay, that's correct answer now. Okay. Tricky problem. It was a bit more case basher, but still like reasonable amount of cases. It could be much worse. Like if k is allowed to be like at least at most h plus w plus 1, it would be worse, but probably not by a lot. But if like plus 2, it would be much worse. I'm sure like it's still possible to do in constant number of cases, but that constant will be like in the tens, if not hundreds. Right. Next problem D. Insert XOR. There is an integer sequence A of length n consisting of zeros and ones. You are given q queries. The q's query is as follows. An integer I between 1 and n is given. Change ai to 1 if it was 0 and to 0 if it was 1. Okay. After processing each query, find the answer to the following problem. Consider sequences B from 1 to size of B consisting of zeros and ones that satisfy the following condition. By performing the following operation any number of times on B, it can be made to match sequence A. Choose an integer I between 1 and size of B minus 1 inclusive. Insert XOR of those two elements between them. It can be proved that there always exists a B that satisfies the condition. Sure, sequence A satisfies that condition. Find the minimum possible value of B. Okay, so we need to... Why couldn't they write it normally? Like, we can look at the operations in the reverse order, and it means that like I can remove an element from the sequence if it is equal to XOR of its two neighbors. We start with A, or like we should start with B of minimal size and end up with A, But if we look at it in reverse order, we start with A, remove some elements, and we want to like arrive at minimum possible size, or like do as many operations as possible. So yeah, we have an integer sequence A of zeros and ones. We can like repeatedly remove an element if it is equal to XOR of its two neighbors at the moment. We want to do as many operations as possible, find like how many operations we can do, and now we need to do it on like change in sequence. So first we need to understand how to solve one query. So if I have like 0, 0, 0, I can remove it. If I have 0, 1, 1, I can remove 1. If I have 1, 1, 0, I can remove 1. If I have 1, 0, 1, I can remove 0. Okay, so like those two look like if we have like segment of ones, we can reduce it to just one. If it is surrounded by zeros, or I guess we just need 0 on one side. If there is a 0 on one side, we can remove one here, then remove this one, remove this one, remove this one, and so on, until we left with just one segment of length ones. But we cannot fully remove segment of ones. So yeah, it seems that we just need to look at those segments of ones and zeros. So we have some zeros, we have some ones, some zeros, some ones. We can have like just 1 0, we have some ones, a lot of zeros, and so on. So if we have just 1 0 between ones, we can remove it and merge those two segments of ones. Every segment of ones we will just cut down to one element. And if we have like a long sequence of long segment of zeros, we can cut it down to 2 zeros using this. Like we can take 3 consecutive zeros and remove the middle one. So basically we're interested in like what's the leftmost symbol and what's the rightmost symbol, because like on the ends like there are some shenanigans. We are also interested in the number of segments of zeros that are of length at least 2, because them we can only like reduce to 2 zeros, and then we cannot do anything about it. Like if we have like 1 0 0 1, we cannot reduce those 2 zeros. None of them can be removed and never will be, because like both of those ones will stay there forever. Like, we can remove them maybe, but they will be replaced by more ones. Never will become 0 here. So yeah, those segments of zeros will be reduced to length 2. All other zeros that are like standalone, we will just cut them down because they're between segments of ones, and then we collapse those. So basically at the end our sequence will be like those segments of zeros that were long, we will cut them down to 2, and ones between them. And like on the ends, it can be somewhat tricky. Like there can be just 1 0 on the end, because we cannot remove it because it is not surrounded by ones. But that's shouldn't be a big issue. We just want to know like what's the length of that thing and what is on the borders. And I think we can just store that in the segment tree and merge those two things and do updates in the segment tree. What a dumb problem. I mean, I don't know. It's okay, but no. Just like understand how it is reduced and then write a segment tree. Not what I would expect from a coder. I guess there is also like case when they're all ones, and then we cannot do anything about it. We cannot do any operation from the start. Okay, let's just implement that. Doesn't seem like interesting. Maybe look at problem E, and then we will come back to D. Problem E, tile grid with 1 hole. There is a grid with H rows and W columns, where the cell at the ith row from the top and jth column from the left is denoted as ij. The grid has a hole only in cell RC. We will tile all cells without a hole using several tiles. You are given non-negative integers n and m such that h times w is equal to l times n plus m plus 1. What? Why? Okay. A tile of 1 row and L columns is called a horizontal tile, and tile of L rows and 1 column is called a vertical tile. Oh, okay. We will place like those rectangles 1 by L, and there will be like n horizontal rectangles and m vertical rectangles, and there is also one cell that is a hole. Okay. Determine whether there exists a way to tile using exactly n horizontal tiles and m vertical tiles without rotation, and also show one such way if it exists. For details on the output format and more precise conditions, check the output section. Okay, so this looks like some bullshit constructive. Can we look at some picture? Okay. Could have provided a better picture, but Okay, this will do. So this is a like 3 by 3 grid. L is 2, so we are using rectangles of length 2. We're using 3 vertical and 1 horizontal. And this cell is a hole. Back to problem D. Okay, let's implement that. So basically I just need segment 3. Okay, so have a segment 3, like underlying things are either zeros or ones, and I'm doing like updates and points. All that remains to do is to implement the class of the thing that I'm storing in segment 3. I need to like understand what corresponds to 0 and 1, like what do I need to store and how to merge them. That's pretty much it. So the things that I'm storing in segment 3 is the state of the segment after I compressed as much as possible. There should be some special states for when the segment is all ones or all zeros. If that's not the case, then it should be the general case, and I need to store what's my left border and what's my right border. Oh, there is probably some interesting thing when I have a zero, but I don't have long segments of zeros. So something like this. Then I can reduce all the segments of ones to length 1, because I do have zeros on borders. So I get there, then I can remove a 0, and then again reduce the segment of ones to 1. So I can get to 1, 0, 1, and then I can remove the 0. But I cannot do anything else, obviously. Do I have to store that separately, or is it just general case, but I don't have only ones? So yeah, general case, and I will just have ones on ends. I think it should be okay to store it as general case. Just remember that the answer cannot be 1. N is at least 3. So yeah, if I have this two, if I just left with 2 elements, I cannot remove anything. So if the tree says that the answer is 1, the actual answer is 2. So all zeros is also not a special case, actually. So the only special case is whether it's true that it's all ones. If yes, then len will be just the number of ones, and that's it. Len, and I need to know what are my groups on the left border and on the right border. And the possible groups are some number of ones, which will be just stored as 1. And I can compress all of them. If it is not the special case, it means that I have 0, so I can compress every group of ones into just one element. Now, if I have zeros on the end, it is either just 1 0 or it's several zeros. Several zeros are compressed into 2 zeros, but just single 0 is not compressed. And if it will be sandwiched between ones, like I can remove it and then compress the ones. So I have 3 cases, and I will denote them by 0, 1, 2, which means just a 0, just a 1, and 2 or more zeros. Not a great notation, but it is just numbers 0, 1, 2, and it is like logical for me, so I will stick to it. Okay, let's say that empty is all ones and there are 0 of them. Not the best strategy. Probably should have created like a separate thing where like it's just empty. Let's do it. Although like length equal to 0 is for non-empty segments that cannot happen, so length equal to 0 is the same as empty. Okay. I might need some other constructor, but I don't know. Okay, so if a len is 0, just return this, because that means that the thing that I'm merging with is empty. If my len is 0, then the answer is just A. If all ones and A all ones, it means that we had all ones and the other also all ones, so their merge is still all ones and the length is just the sum of lengths. Otherwise, it is not true that it's all ones, but for those that were all ones, I was storing length, and I don't want to do that anymore. I want to treat those all ones as just one group of ones which will be compressed to just segment of length 1. So I want to set length to 1 if it was all ones. I cannot do that because it's const. Okay, let's just copy. So the result will be not all ones. So I have like this left thing, I'm adding thing on the right. The length of the result will be like more or less sum of lengths, except like on the like gluing point there can be some reductions that we need to address. So if why those cases? Because 0 and 2 are both groups of zeros, so they will be merged like similarly. And also if we are merging two groups of zeros, even if they were small before the merge, they will be big after the merge. So the resulting group will always be like big group of zeros. There will be like some differences because of how length is calculated, but it is like small ifs, but and those are kind of big. So we have cases like 1, 1, 1 and zeros, zeros and 1, and zeros and zeros. So 1, 1 just means that those groups of ones will be merged. Before the merge, each of them contributed 1 to length. We summed them up, but after the merge they also contribute just 1, so we added 2 for that group and we need to add 1, so we need to do len minus minus. Okay, here we will have more cases, I guess. Well, yeah, sure. So I had a group of ones, then just single zero, and then group of ones. Probably. Actually. Maybe all zeros is also important. No. If it was a group of ones, then 0, and then more ones, then I will be able to slash that 0 and then merge those group of ones, so len will be reduced by 2. But if it was just a 0, and I won't be able to do that. I guess I can check it like by checking the length of the segment. If length is 1, that means that I had it 0 and nothing else. So in this case, I'm just saying that I'm now ending with 0, single 0, and that's it. Oh, this is going great. This will be easy to debug. Otherwise, I can cut that 0 and then merge group of 1, so length is decreased by 2. I'm ending on what the other thing was ending, and that's it. Now, if I had ones and the other had group of zeros, then nothing happens. Just I'm ending what they were ending. That's it. Now this case should be symmetrical to this case, which means that I need to do if on whether R was 0 or not. If it was 2, then everything is good. Otherwise, if my length was 1, then I will start with a single 0 and end on whatever they were ending. Otherwise, I ended on a single 0. There were 1s there, so I'm just doing normal things. Okay, and now the case when I merge two segments of zeros. Those segments of zeros will become one long segment of zeros. And actually, yeah, if I was only zeros, that would matter. Great. This is just great. Another great thing is that I'm like rewriting the left one because like I'm doing in place plus equal. So I need to think about like the order I'm checking what was the old values and writing the new ones. Yeah, this is such a bad way to write this code. Don't do that at home. So in the normal situation, what would happen? if I had a single zero on the border, it contributed 1 to length, otherwise, like the segment of zeros contributed 2. The same on the other side. After the merge, they will contribute 2. So, also I increased length here, but I'm checking length here. That's not good. Not good at all. I think I need to stop and rethink what I'm doing and come up with a better way of doing this. Okay, so first of all, I will switch to writing operator plus with 2 constant. Also, I don't want them to be constant. It's crazy that's the first time I encountered like the problem where the thing I want to write inside this plus equal operator for the segment tree is so crazy that my template is not good for it. I mean, I know that my template is not good in general. Probably using lambdas is better. But up to this point, I was able to push through and like didn't have any. I didn't want to do it differently. Like now, this is so bad that I want to do it differently. But I think I will just have to stick with it. I'm kind of close to the end, so I'll just need to push through. Need to like fix that by saying that I have all the languages done. So, yeah, if it was a single zero, it contributed 1. If it was more than single zero, it contributed 2. I summed them up, and the result should contribute 2. So basically, if I just say that if it wasn't a single zero, I subtract 1, it will be correct, because like single zero plus single zero was like 1 plus 1, it will be 2. If it was like 2 plus 1, it will be 3, but I will subtract 1 and get 2, which is what I want. 0 and 2 zeros will be 1 plus 2 minus 1, and 2 plus 2 minus 1 minus 1 will be again 2. So if n was 2 len minus minus, if bl was 2 len minus minus. Okay, now those emerged, but I also have, so they're kind of in the middle. So on the left is the group I had on the left, and on the right is the group that the other one had on the right. Correct? Not exactly, because maybe they were the same group. Like if it was just one group, they will they were the same group, so those zeros merged and it's now a group of several zeros, so maybe on the left and on the right we have those now. So that is what I should do generally, but also if old len was 1, then like my whole left segment was just 1 0, now it's like 0 and then several zeros here, so they merged, so my left group is actually several zeros. And if blen was 1, then my right group is actually 2. Okay, this like kind of should work, but it's so bad that it probably shouldn't work, and if it will be kind of surprising. Well, it doesn't, so things as they should be, I guess. Also, no, yeah, oh yeah, I didn't set 0 and 1. So what is 0? 0 all ones is false. 0 len is 1, and 0 left and 0 right is just 1 0. 1 all ones is true. 1 len is 1, and 1 left, 1 right are just ones. Okay, it works in samples, which is incredible. I'm hoping that it will not be accepted, because if it is, you will get a wrong idea from that. Yay, it is not accepted. Although, like, it was run cancer on second test. Wasn't second test the sample? Okay, I guess not. So yeah, it works on samples. It doesn't work on general tests. That's good. I mean, it shouldn't be like far from truth. Yeah, let's also change to get because I wrote this badly and it works for only for commutative functions, I think. Yeah, my template kind of sucks. Figuring that out live. I mean, that should have been true. Didn't copy R here. That was not a good way to solve this problem. I mean, the solution is correct, and I'm like 99% sure that that's the intended way. That like you need to maintain the condensed versions, and the way to do that is to maintain length, what's on the left, what's on the right, and like a couple of special cases like all ones. But the way I wrote this function is awful. Don't do that. They have 24 minutes for this constructive bullshit. I don't want to do this. Have a grid, hole in one cell, horizontal and vertical rectangles 1 by L, have given number of horizontal and vertical rectangles, so I can't even just cover how I want. There was a similar problem on Timus, like something about symmetry. There was a whole contest about symmetries for some reason. I think you needed to say like what is the largest number of cells you can cover with like rectangles 1 by something, but the cell that is absent was not given, and you could rotate rectangles how you want, not just n horizontal and m vertical or whatever it is. Maybe it's just not possible in many cases. only non-trivial sample they give is this one. So, okay, when is it clearly possible? For fixed L, let's let's say that our width and height of the rectangle are 1 modulo L. So it's small w times L plus 1, small h times L plus 1. And also the coordinates of the whole are also 1 modulo L. So it's xl plus 1 and yl plus 1 for some x and y. So something like this. Then for some combinations of number of horizontal and vertical rectangles, it is possible. This cell is cut out. Those will be vertical, those will be horizontal, and we have some L by L squares that can be covered with either L vertical planks or L horizontal planks. Now I think like a somewhat reasonable assumption is that in most other cases it is not possible. There is an exception to that, at least one that I know. It's if L is equal to 2, then like in 3 by 3 square, if the middle cell is cut out, we can do like this kind of whirlpool. And then like if it is on some big board with odd sides, basically the cells that I allowed are like half of odd cells. So those are the cells that I could solve like this. But if like this cell or this cell or this cell or this cell or similar cells are holes, it is also possible because, like for example, for this cell we can take a 3 by 3 square with this cell as the center, then solve it, but then continue the solution as if, for example, this cell was missing. If this cell was missing, I would be using like this vertical, this horizontal, and this 2x2 square. Now, like this 3x3 square is different, but everything else I can feel the same way as for this missing cell. What if, for example, this cell was missing? Well, then it's impossible because there is a chess coloring, and every 1x2 square will cover like one black and one white cell, so the cutout one must be black, so that after it we have the same number of white and black. So if L is equal to 2 and the cutout cell is black in this chess coloring, it's always possible for correct combinations of horizontal and vertical. What if, like I'm saying correct combination, what if they're not correct? Actually, it would be not possible, I think. Like, I can show that the parity must be correct, but also, like I'm saying, that I have to use some number of horizontal and some number of vertical, and then the parity will be correct. I don't exactly know how to show that I have to use that number of horizontal and vertical, although probably probably it works. So the idea is that the sides of the grid must be odd, because we cut out one cell and then we want to cover it with 1x2 rectangles, so the number of cells we will cover will be even, so the area of the whole grid must be odd. So both sides must be odd. And we can also look at the number of the parity of the number of cells we need to cover for every column and every row. It is 1 for every column and every row. I'm just talking about L equal to 2. Except where we have like our cutout cells, and it will be 0 in those two. But then if we look at the rows, for example, if we place row dominoes, those parities will not change. But in the end, they will become 0. So we need to change all of them to zeros. And the only way to do it is by placing vertical dominoes. And like each time you place a vertical domino, you flip 2 of them. Yeah, and the 2 you're flipping also have different parities of the row. So the parity of the number of vertical dominoes you place must be correct, and also there is a minimum limit on the number of vertical dominoes you need to turn all the ones into zeros. And my construction achieves those minimums, and for everything between those bounds, it will give a solution. And the same you can do for columns that will provide like minimum limit on horizontal dominoes. So for L equal to 2, I have a like completely correct solution. For all cases it is possible, I will be able to do it. For the cases that is not possible, I will not be able to, I will say that it is not possible. What if L is not 2? I'm saying that I can solve some cases, And I'm kind of hoping that all the other cases are impossible to solve. And the way to show it, I think, would be to use, like, for L equal to 2, we're using chess coloring extensively. For other L's, we will use a coloring in L colors, I think, by the diagonals. Like, cover everything in diagonals. And the diagonal number I we will color in color I. Then every rectangle covers exactly one cell of each color. So after we remove the whole cell, the counts of cells for every color must be the same. And I'm assuming that it's achievable only if both sides are divisible by are given one modulo L. And also the cells that we should cut out will lie on diagonals that are given like 1, that are the same as this corner and all the corners actually. But like I'm saying diagonals, but the cells I'm stating that the solution exists are not just diagonals, they're like those specific things. But with like in addition to this coloring, we can also look at the diagonals in the other direction, and the same will be true for them. So the cells that the solution exists should lie like on specific set of diagonals in one direction and specific set of diagonals in the other direction, and their intersections will be exactly those cells. And like the fact that horizontal and vertical rectangles should be used like at least that many and that many, and the correct remainder modulo L, I'm guessing that they are proven in a similar way to this. So it's not a proof, obviously. Like I need to actually check all of those steps and make sure that I didn't miss anything. But I think that is actually a correct solution. And like it wouldn't be even like very hard to implement, but not in 5 minutes. So I guess I'm done for today. Can take a look at the standings. Yeah, problem E. Some issues. Problem D also not like super easy. And problem C is not super easy. Yeah, it was tricky. And E is a nasty constructive. Alright, thanks for watching. Bye.